Okay, in this video we will look at how we can perform convolution integral using a graphical approach. So although we can find the convolution of two signals using the equation, okay, as in the previous example using equation, however, if the product is very complicated, finding the inverse may be tough. When to do the inverse Laplace transform to transform from frequency domain, S domain to time domain, it will be very difficult to certain examples, certain condition. All right. So and also there are situations in which you only have experimental data. Okay, you perform experimental work, get the data in terms of signals, all right, and there are no explicit Laplace transform. There's no equation for you to work on the solution. So in this case, we have to use convolution integral in time domain format, okay, using the graphical approach. The graphical procedure for evaluating the convolution integral usually involve 4 steps. Okay, these are the steps. 1, 2, 3, 4. First is folding. Then is displacement, multiplication, integration. Okay, we will look at each of these steps in example 1. But before, let's look at example from a website on what is convolution integral using graphical approach. Okay, so here we have this website. Okay, this website, convolution demo and visualization. Okay, you can see here the same thing, convolution integral, right? Equation for the convolution integral. So let's say we have two functions, two waveform, right? So ht and ft. Ht is 2-second pulse, which is this one, all right? It is a pulse with 2-second period, and then we have a second waveform which is 1-second pulse at 2 amplitude, which is this one, 1-second pulse with magnitude or amplitude of 2. Right, so if these two signals or two equations or two functions are integrated, convolution integral, okay, we perform convolution integral on these two waveform or these two functions, what we will obtain is this result. This is the result, or this is the output. Okay, remember, we want to get the output of the system. Okay, so here let's look at how these two signals or these two functions, the output when we perform convolution integral. So you can just slide here, look at this figure. Okay, when we slide from -1 second to 0 to 1 second here, right, and then to 2 seconds, and you can see here that these two signals, when they are both overlapping each other, right, so overlapping each other, you can see that the 2-second pulse is moving. All right, so this is the input, and the pulse that is remain fixed, that is the system. All right, and then finally the output is this, right? So this is the fixed signal, which is the system, and this one is the input, which is moving. Okay, all right, according to the time. And this is the output of the system. So that is the idea of convolution integral using a graphical approach. Okay, the visualization of the convolution integral. Now let's go back to the slide. Right, so you can try to explore this at this website. Right, now let's go to the example. Okay, how can we do this by ourselves using a calculation and drawing of the waveform of the signals? Okay, so we have here two signals here, right? X1 and X2. All right, so how can we convolve these two signals? All right, first is we have to take one signal, which is the input. For example, the input, for example, in this case is X1. Okay, so we take this and fold the signal, right? Folding here, this is the first step. Take the mirror image of H lambda about the ordinate axis to obtain H negative lambda. So means that you fold the signal at y axis here. So the result is this. You fold it, right? You fold it like that. Okay, just fold at the y axis. So we get like that. And then displacement, that is the second step. Displacement, shift or delay the signal. Initially it was x1t, refer to the t, but now since you fold it, we have folded, it is now x1 lambda and negative, right? Negative, referring to the fold. And we use lambda because we want to after this the step is we want to use t, so we change the variable to lambda so that we will not confuse. All right, so let's now assume this is lambda. So this is lambda. All right, so next, the second step is to displace. All right, shift or delay. So what this means is actually this waveform or this signal will move to the right hand side. Move to the right hand side. As you can see here, it moved to the right hand side, slowly moving, step by step. Alright, so here the width of the pulse is 1 second. Alright, now it moved here as much as t can be 0.5 for example, but the width is still 1 second, which is t, this is t, this is t minus 1, so this is still 1 second, right? So that is the second step, displacement. Next is the third step, multiplications. Once we have displaced this, we have to multiply with the x2, right? And then we have to integrate. Now let's look at the third step, which is multiplication. So this is when the first signal has shifted, right? Okay, this is fixed, this is remain fixed at 1, from 1 to 3, it doesn't move, only this signal is moved, or right? So fold it and shift it to the right. So you can see here, now it is shifting to the right. It is shifting to the right. Okay, so now the edge of the signal here, alright, it has moved as much as t. Okay, initially it was from 0, right? Initially it was from 0, now it has moved to t, right? So it has moved to t. Let's say t is 0.5, for example. Let's say this is 0.5. Okay, so from 0 to 1, this is middle, 0.5. So let's say that x1 lambda has moved as much as 0.5. Okay, so when we have to draw this again, we draw this, and these two signals are not overlapping. Okay, no overlap. So when there is no overlap, the convolution, the results yt, alright, yt equals x1t times, or convolution x2t is 0. Okay, because no overlap. That is the first step. Next, we continue to move or delay or to shift the signal x1. It was before between 0 to 1, and now between 1 to 2. Okay, or let's move as much as 1.5, for example. Let's say this is 1, this is 2, this is 1.5, for example, right here in the middle here. So you can see that now x1 has overlap with x2 in this area, right? Let's move to, if you can see here, now it is overlap in this area, this region. Yep. So we have to get the amplitude for these two. Okay, so the signal 1, right, signal 1, the amplitude is 2, which is this. The signal 2, okay, signal 2 amplitude is 1, which is 1. So you multiply this and then you integrate it, okay, with lambda from 1 to t. Alright, take note, from 1 to t. From 1 to t. Why? Because this is the region that has overlap. Okay, right? You only integrate the region where it is overlap. Okay, so in this case from 1 to t. So you integrate to lambda, and then finally you will get this, okay, to t minus 1. So this is actually the result of yt. Okay, so initially, before it was yt, it was 0 for this region from 0 to 1, and now from 1 to 2, yt is 2t minus 1. Okay, so then we continue to move this signal x1 to the next step, which is 2, 3, okay, which is this. Okay, now remember, x2 remain fixed, doesn't move, only x1 move. Now x1 move here, this is 2. Now it has moved here, which is between 2 and 3, right? Between 2 and 3. So here the area that has overlap is this. Same thing, amplitude for this, amplitude multiply with amplitude for this, with this, right? This is what means multiplication, right? Right? So 2 multiply with 1, same thing. However, the difference here is the region of overlapping is from t minus 1, okay, here t minus 1 to t, right? So you do the integration, you will get 2. This is the result for yt. Okay, same thing. Next is to move this to here. Now can see here now x2 is way ahead of x2. Okay, x1 is way ahead of x2, in front of x2. So same thing, 2 times 1, and then the region of overlapping is t minus 1 to 3. T minus 1 to 3. Same thing, you perform this integration, you will get yt equals 8 minus 2t, and for this area, okay, for this shift. Then you continue until these two signals do not overlap. Okay, when there's no overlapping, yt is simply 0, right? And then this is the result you will get. Yt first is 0 for 0 between 0 and 1. Okay, next is 2t minus 2, or 2t, or 2 in bracket t minus 1, same thing, 2t minus 2 for between 1 and 2, right? And then the next is 2, which is this, and then next is 8 minus 2t, this, and then finally 0. And you can actually plot this. Remember, this is actually piecewise function, which we have learned in previous video. This is the piecewise function, so we have to draw this piecewise function. 0 for 0 to 1, 0, 2t minus 2 from 1 to 2, which is this, 2 from 2 to 3, which is this, 8 minus 2t from 3 to 4, which is this. Alright, and then finally 0. Okay, this is the line equation. Okay, 2t minus 2 line equation means that the slope is 2 and crossing at y-axis is negative 2. Okay, it's simple straight line equation. Okay, so this is the answer. Going back to this, you see, this is the answer. In this case, let's change this. 1 second pause. Alright, now you can see that the 1 second pulse that has 2 amplitude is moving, right?